My name is Şehriban Oturan, and as an arts and culture assistant here, I would like to welcome and thank you all for joining us for a very special and inspiring talk by Melih Kamaoğlu. This talk is part of our ongoing Young Scholar Seminar series, which we have been running since 2017 regularly. I'm sure there are some regular companions of us, and I'm sure some of you are here for the first time. So I would like to give a little information about this special and artful institute. As a cultural diplomacy institute, the Yunus Emre Institute was established as a foundation in 2007, with operations beginning in 2009. The aim here to increase awareness of Turkish culture, support the learning of the Turkish language, and stimulate greater exchange in the fields of arts, culture, and science and education, with this one being a beautiful example of it. Named after the famous 13th century poet, Yunus Emre, there are a total of 66 branches across 54 countries. As an institute, we regularly hold a variety of classes and events to teach and promote traditional and contemporary Turkish art and culture. If you haven't seen yet, we launched a very special exhibition yesterday called the Noble Exhibition. It's a collective art exhibition which includes splendid artworks by emerging and established Turkish artists. And it is running from yesterday until the 21st of December, and you're all welcome to visit free of charge from 10 a.m. in the morning and until 6 p.m. I'm not going to keep you long, just to let you know that we are quite active on social media. If you're interested in our events, I highly recommend that you give us a follow on all social media platforms. You can find us as, I'm sure it should be somewhere here, yeah, at YEE Londra on all social media platforms. Now, without further ado, I will highly encourage you all to put your hands together for Melih Kamaoğlu, and let's hear his inspiring findings on the philosophy of nature and architecture.
Well, thank you everyone for coming here tonight, and many thanks to Yunus Emre Institute for having me today and organizing this event. I hope you can hear me clearly. That's great. And yeah, I'm really excited to be here tonight to represent my work at the intersection of actually my master's thesis and PhD research. The title of my presentation is Philosophy of Nature and Architecture in the Age of Computation. In the first part of the presentation, I will explain the historical and theoretical and, in a way, philosophical background of the research to make it clear what I mean by philosophy of nature and what I mean by architecture and computation. And after this historical background, I will direct the focus on 21st century and how architects are understanding nature today and how they are reflecting the idea of nature in architectural design by using computation as a kind of bridge and sometimes as a tool. Of course, this relationship between the philosophy of nature and architecture starts right away after we started to appear on the world, right away when we started to evolve actually in the planet Earth. And as you know, we always question the reality of nature to understand how it works and to also make sense our existence in the world and in the universe. And we used to consider nature as a source of intelligence and inspiration to solve the problems we have, and creativity, right, which have undeniable effects on what we design, how we design, and what we make, how we make. And in a way, imitation of nature in terms of form, structure, material, system, and organization was inevitable for us as a human action. Because there is a comprehensive interrelationship between the philosophy of nature and architectural design procedures. And the philosophy of nature is also related with how designer understands the world and the nature around us. In other words, the way we perceive the reality of nature determines how we design the world. Because philosophy of nature is about how you understand and how you make sense of the world around us. And from prehistoric times to ancient Greek, to Renaissance, to 21st century, varieties of philosophy of nature have played a vital role in shaping architectural design theories and practices. Of course, during the initial stages of human evolution, this relationship was very simple, and it was shaped by primitive man's understanding of nature, kill or die, something like that, and use the animal tools and so on. But towards the 21st century, this network has been further developed by establishing various relationships with different disciplines like theology, mathematics, geometry, and of course, computational science, which is the key to this presentation. Philosopher and historian Robin George Collingwood categorized divergent conceptions of nature under three fundamental historical periods: the Greek, the Renaissance, and the modern times, which we are in today. In ancient Greek, nature is kind of organism. In the Renaissance, nature is something measurable and kind of quantitative fact. In the modern times, nature is evolutionary process, according to Collingwood. And if you focus on ancient Greek, nature was conceived kind of as an organism where there is a mind, and the mind's existence is arranging the order in the universe, the idea of logos, to be precise. And to be more specific, for example, there was this idea of essence of the nature is geometrical formation back in ancient Greek, which was coming from Pythagoras. And for example, this idea was reflected in architectural design as the use of primary geometrical forms in architecture. Another example is theory of forms, which was introduced by Plato. And that idea also paved the way to search for ideal forms in building design, again, through the primary geometrical forms. Another one is, of course, the idea of development towards the purpose and completeness in nature, which was emphasized by Aristotle. And this idea led Greek architects to pursue perfection in design and craftsmanship. And therefore, these philosophies of nature is reflected as ratio, symmetry, and primary geometric forms and perfection in architectural design. We need to realize that at this stage, we are just observing nature and trying to understand its processes through our minds. If you look at the picture on the left-hand side, there is a Plato showing the other world, the ideal worlds, and on the right-hand side, there is Aristotle showing this world. And it's all about how you understand the nature with your own mind by observing or some speculating about some metaphysical world. So this means that our tool, agency, and the medium to understand nature is minds, and our mind and its reasonings. But when it comes to Renaissance, we started to examine nature through the laws of nature with the developments in pre-modern science, which was aiming to explain the universe by measurable and quantitative facts. And of course, because of this philosophy of nature, Renaissance architects started to perceive architecture as a mathematics-based discipline. They employed the rules of perspective, for example, as a scientific analysis of universal space. And they believed that the ideal system of proportions could be created by combining, again, primary geometric forms. Again, it's about Plato and Pythagoras. And therefore, this architectural language emerged, which pays attention to ideal proportions, symmetry, and the part-to-whole relationship. In the Renaissance, nature started to be perceived like a machine, having some specific designed parts for a specific function by God as a kind of external factor. What is important in here is that there is this analogy between how machine works and how living nature works. For this reason, machine actually is a tool, a medium, an agency that help us better understand nature through and reflected in the world as a physical models. And ultimately, of course, for the modern times, evolution theory is the essential transformative power in understanding of nature today. Of course, Collingwood didn't see what happened after 1940s because he died. And probably he didn't have a chance to appreciate one of the greatest tools of the humans regarding the connection to nature, which is computers and the computation. And it is key to this presentation. Of course, evolution theory was definitely an exceptional scientific development founded upon this concept of process in the living world. And before the introduction of evolution theory, the general assumption was that all living creatures are static, unchanging, non-transformable beings that shows a degree of perfection in the ladder of being, as you can see in the picture. And as you know, Charles Darwin developed the first, in a way, first scientific explanation of how species evolve through successive generations. And therefore, living creatures started to be understood as a changing, evolving, and developing dynamic entities under the influence of natural mechanisms. Darwin explains such a critical paradigm change at the end of his revolutionary book on the origin of species, published in 1859. I just wanted to focus on the last sentence. From so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. This paradigm is at the center of the understanding of nature today. Of course, in time, the working principles of evolutionary mechanisms started to be explained from genetic code to organism to environmental level, thanks to the developments in genetics and developmental biology. But the impact of evolutionary theory has not been limited to biology discipline, because the advancements in the computer science since the 1930s made it possible to create mathematical models of evolutionary processes from the population scale by representing their computational equivalents. For example, Alan Turing defined a theoretical framework for an abstract logical machine that could compute any computable function. And he also investigated mathematical models of the morphogenesis process. Another one is John von Neumann, who recognized this universal computing machine and developed this into the systematic theory of automata, kind of an analogy between how natural systems work and how computers work. And of course, after the 1980s, Stephen Wolfram advanced this idea of universal computer by introducing cellular automation system. And this system actually can create some sort of complex arrangements, including the evolution of life, by following some simple dynamical rules. And depending on the modern synthesis of evolution theory, John Holland, another important one, invented genetic algorithms and built an abstract and universal framework for the evolutionary process inside the computer as a code. But of course, later, various evolutionary algorithms developed depending on the Darwinian model of evolution to apply to various design problems. computer scientists have been interested in utilizing mathematical models of natural evolution because its logic of searching through variations can be used to solve computational problems. And it can be used to adapt your solution into the different variable environments. Of course, these various digital computation models have been capable of providing abstracted representations of natural evolution. It is not the real evolution in nature. It is the abstraction that simplifying and approximating the complexity of life into information bits, I would say. But of course, beyond these digital computation models, the evolutionary process in nature have also been explored through unconventional computing systems, basically by utilizing natural features and the processes of non-living and living materials to develop some sort of non-standard algorithms, I would say, and computation procedures. This is not the one we know. This is not the computer we are using today. This is a different kind of computer. It is chemical computer, I would say. A critical potential of these approaches is to take advantage of emergent behavior, self-organization, and fault tolerance and efficiency in natural systems without abstracting these into qualities of logical statements, which is our computer is about. And finally, after the early 1990s, architects started to utilize evolutionary process in design procedures by instrumentalizing natural evolution, evolution theories, philosophies, computational models of evolution, basically to represent and embed the complexity, randomness, variation, and nonlinearity of nature in architecture. And after 1990s, this generative and responsive comprehension of the form and the shift from individual to collectives promoted a bottom-up approach to design in which the architectural form is produced through sequences of events depending on some local rules. And of course, the increasing power of digital computation after 1990s allowed architects to use this evolutionary logic of try and error in design as a kind of form-finding process in which the full authority of the designer is actually undermined, because in this process, as a designer, we are not just designing the building and the form. The computer is also doing the job, partially, I would say. And of course, the integration of living and non-living materials and their simulations through computation into design process paved the way this idea of kind of unification between what is digital and what is natural in architectural design. And therefore, the evolutionary understanding of nature through computation has become an essential element of architecture today. So this is actually what I'm doing in my PhD research. I'm focusing on the historical process starting from 1990s to today. And I'm looking at how architects are understanding nature today, what kind of computational tools they are using, and how they are reflecting this idea of evolutionary nature in the design. And the aim in here is like foregrounding and critically evaluating this application of natural evolution in digital architecture by using philosophy of computation as a kind of critical tool, because every computational tools have their own limitations and potentials. And by understanding their potentials and limitations, we can understand these design projects more critically, I would say. And in the end, it is all about this interdisciplinary relationship between evolution theories, computation, and digital architecture. For example, if we think about the relationship between evolution as it is in nature, and there is this evolution theories and philosophies, that is not the same thing. Evolution is something going on in nature, but the theories are some sort of theoretical explanations and universal systems explaining the evolutionary process in nature. So we need to understand what kind of evolution we are talking about. Is it the one proposed by Darwin? Is it the one proposed in the symbiosis theory? Is it about morphogenesis processes? We need to understand which one architects are using, because each of them have some reflections on the design process. When it comes to the relationship between evolution theory, philosophies, and computation, this time we need to understand which tools. I mean, is it AI? Is it machine learning? Is it just traditional genetic algorithms? Is it just the evolutionary computation? Or is it there are other digital computational tools? What is it? Is it maybe just material computation? We need to understand which computational tools architects are referring to. That's the key to understand their work critically. And finally, of course, we need to understand why architects are bothering to use computational evolution in design, why it is important for them. Is it for just optimization of the form? Is it to create endless variations of the form by using computation? Is it for bringing the aesthetics in nature into design? Maybe it is also for bringing the cognition and kind of consciousness in nature into architectural design process. All of them have different implications for the design. Now I'm gonna show you 5 examples. Of course, it is not possible to show every architect and their work. So I will just show you 5 examples, hopefully that will summarize various approaches to computational evolution in design. It starts with John Fraser and his book, An Evolutionary Architecture. This book was actually result of 30 years of work at AA. And John Fraser, for example, applied neo-Darwinian understanding of evolution in architectural design by using cellular automation and genetic algorithms. An idea was utilizing dynamic, this self-renewing and responsive characteristics of nature in architecture. And in this system, these form-generating processes were investigated, and all the emerged forms were tested through accelerated virtual evolutionary model, which was shaped by both internal dynamics of genetics and also external dynamics of environmental factors. But I need to warn you, this is all happening inside of the computer. When I say genetics, it is not the real genetics. It is the analogy to how genetics works and how it affects us. And in here, architectural concepts are defined as a kind of generative rules, which corresponds to some sort of form generation processes, which you can see in the slide on the left-hand side, and their evolution tested with the power of computers, actually. And in a way, these forms were unpredictable because these characteristics of randomness was introduced into this bottom-up process and through the variation mechanisms and environmental factors. By coding these natural mechanisms and abstracting these natural principles inside of the computer model. As you can see, from very simple start, like one cell, and there is a complexity of the form, and it is all evolving inside of the computer. And although this system actually can get feedback from the environment, I mean, we can feed it with the environmental data, but this evolving architectural proposition is still inside of the computer. This means that once we decide to build this generated architectural proposition, for example, the one at the end, it won't change in response to the environment once we build it. So this also adaptation and evolution is happening inside of the computer model. Once you build it, it is something static, it's staying there. The other one is Greg Lean and his idea of animation of the form and his project in biological houses. Contrary to John Fraser, Greg Lean was kind of against neo-Darwinian evolutionary model. for its dependence on this mutation, natural selection, and gradualism, and so on. And Greglin accepted actually in the symbiosis theory as the best evolutionary model for architectural design. And he recognized architectural geometry as an evolutionary space where the continuous differential transformations occur. And in here, Greglin promoted the importance of process as endless variations of the form. And if you think about all the forms in the image, all these forms can be considered perfect in their unique context, since this logic of continuous change depending on some external factor was proposed to justify the design solution. And in here, for example, in this project, Greglin first set up some parameters for the geometry, and then he experimented with the evolution of the form by playing with control points of that geometry. And then these geometries are transformed to another application inside of the computer to make it more smooth and the continuous forms. And in here, again, architecture is part of digital simulation regarding its relation to nature until the evolution of the form finalized, at least. And of course, the expectation is not that this architectural form will change and evolve in the real world. Again, this is happening inside of the computer. Another group was Emergent Technologies and Design Group, which is still there at AA, which was founded by Michael Weinstock, Achim Menges, and Michael Hansel. And they together proposed a design methodology in which evolutionary and morphogenetic processes were employed together for higher performance, functionality, and environmental sensitivity. And in here, the idea is also integrating self-organization capacity and the performative capacity of the material in the growth and the evolution of the form I showed you before. Now, it is not just about the abstract definitions of geometry and its evolution. Now, material part plays a key role. And the evolutionary process and randomness wasn't used just to generate some variations of the architectural forms, but to create architectural models where the formal, structural, and the material qualities are considered together, not separately. And therefore, the evolution and the development of the architectural form is not only dependent on these abstract codes that generate and evolve the geometries inside of the computer, but it is also dependent on the physical qualities of material itself. I believe this is one of the progress that demands attention, because through material computation, by considering the physical condition of the material, architecture makes direct connection to the physical world beyond this strict computational form generation simulations. And material itself becomes co-designer in the evolution of the form. The other one is architect Jenny Sabin and biologist Peter Jones. They together analyze the emergence of the natural complexity at different scales. Like I mentioned before, it can be cell structures, it can be morphological change, it can be self-organization. And they also abstracted these models into, again, computational design models inside of the computer. But while doing this, they also focused on this responsiveness of architectural design by exploring the variety of materials and technologies. Let me show you. One of the exciting arguments was understanding design as a kind of continuous evolutionary process of forces instead of objects and their relations. If you remember the first examples, it was all about the object and it was all about its evolution of that form. But in this time, it is not about the form. And therefore, the architectural design as object have only secondary quality of evolutionary design process. And this is allowing a kind of collaborative work of nature, computation, and technology together, not separately, not consecutively. It's happening, all of them happening at the same time. And the idea is material computation on the one side, and also using generative tools, translating and transferring the biological processes and behaviors to these physical models and analog models, I would say. For Jenny Sabin, in this way, computation can be used as a kind of bridge to bring the operation of nature into the architecture. Because in this proposed system, both digital and natural qualities inform the evolution of this form, evolution of this architectural design. And also, this built structure can also respond to environmental factors. So in here, it is not static. It is also responding to, if you go there, you can also play with it, you can change it. Its materials also responding to human action in there. So now the structure itself is responding. It is not just happening inside of the computer. The last example I will share is the phi computation, which was started to be used by architects lately for road networks optimization, for 3D form finding processes, for urban design. Phi folicephalium is an organism. It's a large multi-headed slime mold in a way with tube-like structures. In the slide, you can see it on the right-hand side, how it behaves and how it creates some sort of morphology. And in its plasmodium stage, this organism starts to foraging behavior and creates this tubular network connecting to the food sources in the environment. Phi computation actually representing very important and cutting-edge understanding in which evolutionary and morphological mechanisms are no longer abstracted, but its complex interactions observed in behavior and the material sense of this organism. And in the literature, it is demonstrated that without centralized control, like us, our brains have this centralized control. Without centralized control, Phi polycephalium creates dynamic, adaptive network with efficiency, fault tolerance, and cost, comparing to the existing, for example, rail network system and road systems. As I explained before, with digital computation, we are confined with the limits of these logical statements inside of the computer to define the process of this evolution of the form. But with this one, we are kind of restricted with the behavior and the bias and the cognition of this organism about the design decisions. Even though we can partially direct its movement, but it has its own agency. But of course, it is the beauty and novelty of this kind of computation, because it is allowing the agency of another organism to co-design with you. So as a designer, you are not taking all the responsibility for the design. That organism is also taking full responsibility. But probably it doesn't have any idea about that. And to summarize, digital computation process and natural processes are actually quite different with their distinctive structures, the context, and the principles. But this binary logic of digital computation we use with this laptop is capable of producing complex representations of nature. For this reason, there is an information exchange between what is digital and what is natural. And architects who considered natural and the digital as separate things use these simulations of evolutionary process to produce just endless variations of form and optimize the form and so on. I already mentioned all of the examples. And what is important, these architects were aware that once the evolution, as it is in nature, once we abstract it with the computation, we're just playing with this generalized computational equivalence of the evolution. It is not the same evolution in nature. It is abstract. And then once we do that, our design becomes part of the virtual world, virtual domain, or ontology, whatever you say. And for this reason, they didn't argue this idea of united ontology between digital and the natural, where the artificial forms produced by evolutionary simulations were considered part of the nature. It is not the case. But after architects started to realize the growing power of digital computation and the opportunities of using material computation, non-living or living material, it doesn't matter, this idea of unification between digital and the natural has become more common in the mainstream of the digital architecture, especially after 2010, I would say. And I believe the idea is very exciting, and some architects have already some futuristic vision for this biodigital unification in the built environment. But I believe it is still early for such an argument like biodigital unification, because the proposed design models so far haven't achieved this objective completely for me. And digital and natural ontologies, digital and natural, of course, can become more connected in the built environment in the future. Probably if the dream of this cybernetics in architecture is achieved by setting up this direct feedback between our buildings and the environments. Until then, I believe natural and the digital is likely to have separate ontologies with abstract, approximated, and simplified information exchange in between. But of course, only time will tell whether this objective of biodigital ontology will be another failed experiment or outstanding success in the history of architecture. This is the end of the presentation. Thank you. If we have questions, I think we can get the questions. I hope you enjoyed it.
Any questions?
Before the question, may I ask how many architects are here? Can I see? Oh, okay, good.
Oh, great. Thank you. Oh, no. Okay, I should have formulated my question before getting this microphone. Okay, so when does the agency of the architect return in this process, if at all? Because you've described material and the computer as having agency in this process that you might call an analogy of adaptation. And then within evolution analogies, we have natural selection. And can the agency of the architect return as a form of natural selection, or does that kind of wander into creationism a little bit if we talk about the architect's hand as choosing a kind of final state of one of the variations and crystallizing the process of evolution?
Yeah, that's a very good question and deep question, actually. If I think about the ones with the mathematical models just happening inside of the computer, of course, to create some sort of evolutionary model inside of the computer, first, you need to define that evolutionary process inside of the computer. So actually, humans are still in the process, because, as I said before, it is not the same evolution in nature. You need to define it with the algorithms, and also you need to define your fitness criteria, how you are going to evaluate your design, the evolving forms inside of the computer. So I believe it is the humans are still there in the process, but I think we are dependent on the power of computation to make that process very fast and to see varieties of the options. I think that's the key. But for the other part, when the material and kind of living computation start to take reign, it is becoming very complicated. I mean, I'm really not sure where our control starts and where our control ends. For example, in the last one, we saw in computation, I mean, you're just setting up the environment for that organism to grow and create its morphology, but that's it. I mean, you're putting the food sources for it, and it will do the rest. So you're just dependent on its own judgment about the design, and you're just then translating it to urban design context or to the form finding. In that process, I think, yeah, it is a really critical question mark. Why would I depend on the judgment of the organism? I mean, but this is where it is going. I mean, so the answer to your question can depend on each project, but I think I summarized two points.
Well, quick second part to that. Now that you've started your interview process, which I know it's in early stages, have you experienced or noticed that they're talking more about almost being like a technician of a process and a technician of a workflow, or someone that really has a heavy hand in the process?
So far, I had 5 interviews so far, and mostly these interviews were about the first part of the presentation, the one related with just the inside of the computer. So I did not have any interview with the other ones, the ones proposing biodigital ontology. In the interviews, actually, I wasn't surprised too much in the interviews because I already knew their work, but I just started to realize some details that I cannot find in the publications, and I realized that their perspective also was changing. I mean, I was asking questions about the design work that was happened 30 years ago, but I was also asking them about, okay, what do you think about it today? And I believe, I mean, just 5 interviews, but I realized that they are more close to this biodigital idea today. I think they see the future in it in a way. But there are some parts they are not agreeing with each other. Of course, you know, every architect have their own perspective on this. But I think the idea of just form generation, evolving the form inside of the computer will be obsolete in the near future. Of course, we're gonna still do that, but it won't be very excited like the ones with the biodigital one, I guess. But it is hard to say right now because just 5 interviews so far. So thank you.
Thank you for the presentation, Melih. I would like to ask about you mainly mentioned about the understanding of the form of architecture. I know it's the context of this research and how this nature understanding, you know, reflected to the ultimate understanding of architect's form creation. But I wonder what you would like to say about the, you know, social life of this understanding, because it's, you know, these form changes from the, you know, Greek to modern era, you know, changed the, you know, affected the social life of people and users. And in the evaluation of the nature, the agents are the real, you know, part of this process. And it seems much more bottom-up approach while changing their role. But in this understanding, the architects and the form creators have a kind of a top-down, you know, approach while creating these forms. So, you know, all of these designs offer different layouts, you know, different flexibilities. So what can you say about the user's approach? I mean, is there any examples they include users as an agents?
Of course, not in this presentation, but for example, the one with the John Fraser, which happened in 1990s, that wasn't essentially just about having feedback from nature and so on. Some of the users were able to make effect on the system. There was a feedback from the users and also from internet, but that feedback was limited to playing with the genetics of genetical computational explanation of genetics inside of the computer. So users were trying to change the genetic sequence of the form, for example, then the form was changing depending on their reaction. I mean, their effect was there. I mean, users were able to play with that, not just architect, not just designer, but for example, the others can come in and they can play with the form and they can be involved in the process. For example, I remember this one, and the other one is, I think, the Jenny Sabin. For example, in those structures, it is not just about how we can make connection between nature and the structure. Of course, as a user, when you go there, depending on your involvement with those structures, it is responding to you in a way. So of course, in the end, this structure is still for humans. I mean, we cannot just reduce it into, oh, what is the relationship between nature and architecture and so on. In a way, architecture is human action. So of course, designers are also thinking about that. These two examples just came to my mind right now, but if I remember anything else, I can tell you later.
Thank you.
Thank you.
It is working, yes. How much do you think the evolution of 3D printing could help to pass from the abstract part of the evolution to the real world?
You said 3D printing, right?
Yes.
Yeah. I think 3D printing technologies are much more related to the ones I mentioned in the second part of the presentation, the ones with the Biodigital, because it is helping us to have much more precise models about what we want to have in that model. And it is giving us, by using robotics and so on, it is giving us the feeling of being more precise about the form. But I don't think the 3D printing is very related with the ones just mathematical and geometry evolution of the form inside of the computer. So I think 3D printing is much more related to the ones where we are going right now, and it is key, because I mean, I didn't mention about it because I didn't want to make it too technical presentation, but of course it plays a key role, I can say, yeah. I guess that's it.
Thank you, Melih. I just had a question. Artificial intelligence is obviously kind of advancing very quickly, and it sort of makes us kind of question what kind of intelligences are being developed, because it's sort of fashioned after an idea of the human mind, but then there's these other kinds of intelligences, which I think you touched on, that people are finding in terms of how organisms and ecosystems behave, you know, woodlands and trees, and sort of these are being defined as other kinds of feedback intelligence. And so I was wondering whether you felt in sort of medium to long term, whether this division between kind of the natural and the non-natural, whether you see that as something that will be reinforced or eroded, particularly in terms of, we've sort of traditionally defined things in that way. That's obviously where you started, but is this something we're kind of trying to keep, or do you think it might change?
Yeah, again, deep question. I just want to show you, depending on this question, I need to show it. You see the project Gunfisarium on the right-hand side? Yeah. For example, in this one, artificial intelligence was used to observe the behavior of this organism, then translating it into machine learning algorithm and so on. But in the end, the question for me, okay, after this process, after extracting this algorithm and so on, when you built it, what's that? It is still just a static form and it won't change. You can do whatever you want inside of the computer with the algorithm, any adaptational process, evolutionary process. So, I mean, I don't want to be too strict, but I believe the difference between natural and the artificial is still valid. There is no blurry boundary for me. I don't know, maybe in the future it will be more blurred, but I don't agree with the idea that artificial intelligence is blurring the boundaries, what is natural and what is artificial, at least so far, I would say, because we still don't have the consciousness and the cognition in the nature, in artificial intelligence. you know the topic better than me, but this is my perspective so far, because we still don't have that complexity as far as I understand. But in the future, why not? I mean, I'm not closing the door, but so far, for me, natural and the digital and artificial intelligence, it is different things. It has different working systems, but there can be, of course, information exchange in between, which I showed, but still different things for me. Yeah. Thank you.
So it's about, you showed us four broad topics that are related to each other, like evolution is related to evolution philosophy, and digital architecture is like they're all related. And you said we need to understand why architects want to do this, why they develop these forms. Do we have an idea why actually they do it? Is it for pushing the limits? Is it searching for new aesthetics? Do we know anything about that?
Of course, we know, of course. If I turn back to that slide, it will be much more precise. Just a second, bear with me. The last one. I said, for example, optimization. It can be just about optimizing your form, architectural form, depending on some sort of requirements about your building. And this optimization one is much more related to the ones inside of the computer, just the simulation and models. When it comes to variation, as I showed with John Fraser and Greg Lean, it's all about experimenting with what kind of variations we can see from the simple start to the complex form. And when it comes to today, this is a very good question. It is not about just creating variation and so on. Today, as you know, for architects, nature was always a big deal, you know, how we can make sense of the nature and so on. So today, after having these tools and different materials and the technologies, they believe that, at least some of them believes that we can kind of integrate nature and the built environment, and we can solve the sustainability problem maybe with this, and we can respond to climate change with this and so on. There are, of course, other reasons, but I believe it is all about what you have under your desk. I mean, for the people in 1990s, they didn't have the tools we have today. So they were not able to think about within this complexity. But today, architects are acting with these tools. And yeah, in a way, they're just trying to respond to urgent matters of today's architecture, I guess. Yeah.
Thank you.
Thank you.
Hello. So I'm an architect who's studying biodesign right now. So everything that you showed is highly relevant to what I'm studying. It's not much of a question rather than just a comment. So basically, while I'm studying, the challenges that I see are coming from this lab environment to the real world. So the scaling up of the research is the biggest challenge that we have. And that is the reason it is still in this uncertain phase. Oh, does this work? Does this not work? Because for it to come to the user to be used, it takes a lot of optimization, like you said. And another comment about the computation, it is highly relevant, and we are very dependent on computation for predicting these things, because natural organisms and natural things that happen, I mean, we do study about it, but looking at them, it's a time consuming process. So for us to predict them, computation is highly important, and that is where it comes in. And I think it's helping biodigital architecture evolve much faster, because we're able to show, yeah, in 20 years, 30 years, this is how it's going to look. So be happy. So yeah, it was just a comment, and thank you very much for the presentation. It was really helpful.
Thank you for this contribution. Actually, biointegrated design was part of the presentation, but I had to take it out in the last moment because otherwise I'm going to talk for 2 hours. So I didn't want to do that, but it is highly relevant. And the biggest problem is scaling up. That's the biggest problem. I mean, maybe something is working in the scale, but it's not going to work in the building scale, for example. And about, yeah, as you said, computation is very important to predict the living creatures, how they're going to behave and so on. But for me, it is technically impossible to predict the living creatures, not 100%. Of course, you can have some implications from observing it, but that doesn't mean that it's going to behave in the same way in the next time. That's the agency of the nature. I think that is also one of the distinction between the artificial one and the natural one, actually. Thank you.
Thank you for the talk. Could you comment on the evolutionary process, the human brain, whether or not the human brain is also pushing that evolutionary process, in which case, with machine learning, you've currently got GPT-3 generative models using neural network techniques. Could you comment on that?
You mean, repeat which one?
GPT-3. So you have generative models, machine learning models that will generate
that is the technical one, actually. I don't know specifically that. But I can talk about the first part. I mean, I'm not very knowledgeable about specifically about machine learning, but about, where is the human involvement in this evolutionary process? Maybe I can comment on that. Again, if we think about the first part of the presentation, the one with just the evolution of the form and the geometries, if we think about that, like I said before, human action is not, I mean, it is still there because you need to define the rules for the evolution of that form, and also you need to define the rules how you're going to evaluate it, and also you need to define what kind, if you're going to build it, also you need to define what kind of material you're going to use and so on. So I think human action is still there, so it is not missing. As I said before, evolution inside of the computer is not the same evolution in nature. We are just abstracting the principles and putting it into computation, and we are trying to make use of it in a way. But about the machine learning, honestly, I'm not specifically have information about the model you just mentioned, so I cannot give any feedback specific to that model right now. But I would like to have a conversation after this. That would be great. Thank you.
Okay, if there is no question, I would like to thank Melih about the wonderful presentation. For me, as not being an architect, it will take so much time to digest this information. When you were talking about these models, I was thinking about some, traditional theories like vernacular architecture and so forth. Thinking about how you relate the built environment and the nature, but obviously this is totally different, obviously connected to each other. Thank you very much for this presentation. Some of the attendees like me, if they are not architect, obviously I hope they get some inspiration to look into this further. Thank you very much, Melih. Thank you.
My pleasure. Thank you.